Hello again, everybody. This is our video solution to problem 2 from Quiz 10, Spring 2023, Math 302 at Cal State Fullerton. And in this problem, we're back to just talking about functions and relations. And let's see what the problem says. So first, right. Yes, we recall that in calculus, we learned that e to the x and the natural log of x are inverse functions to each other. So in part A, we're asked to give just the domain and the range of these functions. So maybe to help that out a bit, it would be useful to sketch a graph of these functions. So let's see here. So first, the exponential function, e to the x. This is going to look like so. Crosses at 1. You have e to the x. And then the natural log of x being the inverse, we know that it'll be the reflection across the line y equals x. So this looks like here, and loop, something like that. All right, so that'll be natural log of x, and of course it's again going to cross at 1. All right, so now if we're trying to write down, say for e to the x, the domain, well, you can put anything into an exponential, right? There's no real number that's going to break this exponential function. So we could write the domain is all real numbers, or we could write, say negative infinity to infinity, that interval, whatever we like. All right, how about the range? Well, the exponential function is never ever going to give you a negative output. It also is never going to give you 0 as an output. So the range is going to be all of the positive real numbers, or in interval notation, the interval from 0 to infinity. Okay, how about the natural log of x? Well, the natural log of x is the inverse function, which means we can just take the domain and the range, and we can swap them. Okay, we also could look at the graph of the natural log function and see it, but let's see. So you see here from the graph, right, you cannot put anything negative or even 0 into the natural log function. And so you get 0 to infinity, right, which is just the range of e to the x. So this is going to be the positive reals. But as far as outputs, yeah, you can get every possible real number. Okay, so we just swap the domain and the range. Nice. Okay, so that's our answer to part A. How about part B? Let's see. So for part B, we ask for each of these functions, so e to the x and ln of x. Actually, maybe we can just put this into this table here. Determine whether we're injective, surjective, or bijective. Okay, well, let's see here. So first, how about injective? Well, your function is injective if every output has a unique preimage, right? Or if you like, every element of the codomain, which for e to the x, right, our range is the positive reals, but we could take the codomain to be all reals if we liked, or even if we wanted all the positive reals, it doesn't matter as long as it contains the range. But the point here is everything that is an image must have at most one preimage. And if we look at the graph of e to the x, we can see it's an increasing function. So absolutely, there is no y value that is going to be hit twice by e to the x. And so the answer is yes, it is injective. How about surjective? So surjectivity is a bit interesting here, right? This is going to depend on how we actually define the codomain. So this is something that you could argue it either is surjective, right? Because yes, if I just look at the range as my codomain, then I win. And if I take the codomain to be all real numbers, then no, we're not hitting any of the negatives. We're not hitting 0. Okay, so we have to have a little explanation here. Okay, so explanation. So if I think of e to the x as a function, from the reals to the reals, then this is not surjective. Since, for example, 0 has no preimage. But if I think of e to the x as a function from the reals to the positive reals, then it is surjective. Okay, and you say, well, which one is it? Well, I don't know. Depends on which exponential you want to write down. All right, that's up to you. Okay, so now what about bijective? Well, we know that you're bijective if you're both injective and surjective. So this again is a yes-no, but they should be consistent with your answers from above. So if you chose, for example, the codomain to be all real numbers, then you know it's not surjective, and so it's also not bijective. On the other hand, if you chose the one where the codomain is the positive reals, well, then it is surjective, and consequently, because we already know it's injective, it will also be bijective. Okay, so what about for the natural log? Well, for the natural log, injective, yeah, we can see from the graph, there's no repetitions because this is, again, an increasing function. So yes, this is an injective function. How about surjective? Well, yeah, actually, our range is all real numbers. Okay, that means every real number has a preimage, so the answer is yes again. And because it is both injective and surjective, then the answer is going to be yes to being bijective. Okay, so we got B taken care of. All right, how about C? It looks like we want to determine whether, oh, now this is a different function, whether x e to the x is invertible. Okay, well, again, this might depend a little bit on how we choose our codomain, but let's explore this function. Now, there's some information given here. We're told that the domain is all real numbers. Oh, okay. Oh, and we're given the derivative. Well, why are we given the derivative here? Well, if we want to test invertibility, we know we can test whether or not the function is bijective. Okay, so this is an important result. All right, bijective is equivalent to being invertible. And we know that bijective is equivalent to being injective and surjective. So in order to test whether or not x e to the x is invertible, we can test whether or not it's injective and surjective. Now again, that surjective bit will possibly depend on our codomain. But before we even think about that complication, let's think about the injectivity. So injectivity, again, says every element of the range is going to have at most one preimage. Now, if we go back to the graph of e to the x, we saw we could test invertibility by using, or rather injectivity, by using horizontal lines. We can just pick some, y values, right? Any y value, and ask, does this horizontal line cross the graph twice? Because if it does, that means you would have multiple x's corresponding to the same y. Multiple x's, that means multiple preimages for the same output. So if we can see whether the graph has maybe it's increasing, then we could say that this was invertible. Okay, so let's try to graph this function, and we'll use this derivative because, right, derivatives can be used for graphing. So if I try to graph this function, so this is going to be x e to the x as our function, I know the derivative is e to the x times 1 plus x. So where is the derivative 0? So e to the x times 1 plus x is equal to 0. Well, okay, we know e to the x is never equal to 0. So this product can only equal 0 if 1 plus x is equal to 0. But that only happens if x is equal to -1. So we'll add this into our graph. When x is equal to -1, we get, 0. We can graph that. Now, I'm sorry, that's excuse me. That'll be where that's what the derivative will be, but we want to graph the x e to the x. So where will the function be? Well, when x is -1, you get negative e to the -1. Okay, negative e to the -1, that's -1 over e. Okay, that's somewhere down here. Okay, so this is -1 over e. So I know the graph is negative here. When x is 0, I know that the graph is going to cross the axis, because look, 0 times e to the x, or 0 is 0. And now what's going to happen? If we draw a little sine graph for the derivative, so this could be our x e to the x prime sine graph, we know that at -1 we get 0. And what happens when we put in things larger than -1? Like, I don't know, 1,000. 1,000 plus 1 is positive, times e to the 1,000, that's positive. So we get positive here. To the left, when say e is say negative, or x is negative 1,000, we're going to get a negative times, well, an exponential, which is always positive. So this is going to be negative. So this tells me that the graph is going down, right? The graph of x e to the x is going down to the left of -1 and is going up to the right of -1. Okay, so it's going to go down and it's going to go up. Fine. So what does that mean? Well, this is at -1, that's right where it's going to turn around. So it could come down like so and then go up. But if we think about the actual sign of x e to the x, when x is negative, x e to the x is also negative, because we know e to the x is always positive. So actually, even though it has to be going down to the left, it's never going to hit 0 to the left. So it's going to have to look something like this. Right? So it's going to have an asymptote as you go to the left of 0. And it's coming down, and then it's going to rotate, and then it's going to start coming up. Okay? And it can't turn around anymore. So that's roughly speaking what the graph has to look like. Okay, but remember our whole point of this is we wanted to test the injectivity. And because it's going to turn around, right? This graph turns around at -1, we know that we are getting some duplications. There are points to the left and to the right of -1 where we're going to get the exact same value out. So since x e to the x has a local min at -1, we know that there exist points near -1. Say, I don't know, how about A and B, such that A e to the A equals B e to the B. And this implies that x e to the x is not injective, which implies x e to the x is not invertible, because it's not bijective. Okay, so we don't even have to worry about this surjectivity problem here. Right? Okay, so what is the last problem? Is the relation, okay, so it's a subset of R cross R. Looks like pairs, x and y's, where x is y e to the y. So we also could have written this if we'd wanted as all things of the form y e to the y, comma y, where y is an element of R, something like that. So this is essentially asking us, right, if it's going to be a function, we would need that every single element in the domain, which in this case is R, has a unique output, right, a unique image. But we actually just showed that if we write down, for example, A e to the A, that this is exactly equal to B e to the B. And so in the relation that we have up above, we could have A e to the A, comma A. All right, so this would make sense because the what do we need? In the second component, we have some element, and in the first component, we have that element times e to that element. Okay, so I have that, A e to the A. But also, I could have B e to the B, comma B, right? That would be in there as well, right? So both of these, right, are in the relation. Okay, but a e to the a equals b e to the b, which means this piece here is a e to the a comma b. So I have two different input, rather one input that has two distinct outputs. Okay, so this implies that the same input, or the same element, or one element, the element a e to the a has two images, a and b. Therefore, the relation is not a function. And there we go. All right, there's a lot of little things to know, right? Functions are really darn important, but that also means that there's a lot to learn about them. All right, hopefully this is helpful. We'll see you next time.